Hello friends, today I am going to start chapter number 1 of 10th standard real numbers. Real numbers contain integers, whole numbers, natural numbers, rational numbers. I start this chapter by taking a simple division example. Suppose I have a 7 pencils. I want to pack 3 pencils in each box. How many boxes will I need? Is there any pencils remain unboxed? All these answer I got by a simple division method which you learned in your previous standards. Let's start it. How many pencils and boxes? So pencils are 7. I want to pack 3 pencils in each box. How many pencils? 3 pencils in each box. So I need 2 boxes and 1 pencil remain unboxed, right? So how I got this answer? So the answer is by using a simple division method. You divide 7 by 3, right? So 3 2s are 6. You got 7 minus 6, a 1 remainder, right? So here 7 is dividend, 3 is divisor, 2 is quotient and 1 is remainder. This is simple logic of division. There is no new thing will be added of 10th standard. This is the method which you already learned in previous standards. Am I right? Now, so can I say that dividend is equal to divisor multiplied by quotient plus remainder? Dividend is equal to divisor multiplied by quotient plus remainder. In our case, dividend is 7, divisor is 3, quotient is 2 and remainder is 1. So simple, 7 is equal to 3 multiplied by 2 plus 1. 3 2s are 6 plus 1, you got answer 7. So that's why you can say that dividend is equal to divisor multiplied by quotient plus remainder. Now I assign each variable to the divisor, dividend, quotient and remainder. So dividend is equal to A, divisor is equal to B, quotient is equal to Q, and remainder is equal to R. So now A is equal to B multiplied by Q plus R. So A is equal to BQ plus R. So Euclid division lemma are on the base of this particular equation. A is equal to BQ plus R. So let's see the Euclid division lemma. Given positive integers A and B. So there are A and B are the positive integers. There exist unique integer Q and R, satisfying A is equal to BQ plus R. So BQ plus R, which you already know, it is simple division method. So where R is greater than or equal to 0 and less than B. Of course, here remainder is 1. It is always less than your divisor. Remember that friends. Remainder is always less than your divisor. If your remainder is greater than divisor, then automatically you can divide them further. Am I right? So here, if remainder is 1 is always less than your divisor. So here this is the condition which already given. So R is greater than or equal to 0 and less than B. B stands for divisor, right? So here one more word are there, algorithm and lemma. So what is algorithm and lemma? I discuss algorithm because in next some slides you are going to learn about Euclid algorithm. So what is difference between algorithm and lemma? So algorithm is a series of well-defined steps which give a procedure for solving a type of problems. So it is a series of well-defined steps. So by following that step, you can solve your problems, right? And a lemma is proven statement used for proving another statement. So lemma is already proved that, okay, and by that proven statement you can prove another statement. So that is called as a, that particular statement is called as a lemma. Now Euclid division algorithm. Here I mentioned that Euclid division algorithm and what is the use Euclid division algorithm in practice. Means in routine life how you use that Euclid division algorithm. So here, to obtain the HCF of the two positive integers, say a and b, with a is greater than b, follow the steps below. Means Euclid division algorithm is used to find the HCF. HCF stands for highest common factor of any two positive integer. Remember friend, this is used for two positive integers a and b, where a is greater than b. Now how you use that? Let a and b are two numbers, okay. So here a two number is 455 and 42 are the two numbers uh, which we use to find the HCF. So I want to find the HCF of 455 and 42, where 455 is greater than 42. So these are the some steps. So now we start with the step number 1. Apply Euclid's division lemma to A and B. So we find whole number Q and R such that A is equal to BQ plus R. So this is the equation of Euclid lemma, right? And this is the condition 0 is less than or equal to R less than R is less than B, right? Now in our case, you have to find the HCF of 455 and 42. So 455 is your dividend, 42 is your divisor, and 10 is your quotient, and 35 is your remainder. So apply the Euclid lemma on these particular numbers for 455 and 42. So how you got that? So 455 divided by 42. So 455 divided by 42, you got quotient 10 and remainder 35. So I simply represent this by like this, right? Now step number 2. If R equal to 0, B is the HCF of A and B. In our case, this is relates. R not equal to 0, apply the division lemma to B and R. So now in our case, remainder is R is equal to 35, right? So 35 is not equal to 0. So apply the division lemma to B is equal to 42 and R is equal to 35, because B is here divisor here. So divisor is 42 and your remainder was 35, right? So now your divisor become your dividend. So in previous step, 42 is your divisor, right? Now it's become your dividend and your remainder become your divisor. So your 35 it's become your divisor. So now 42 divided by 30, you got quotient 1 and remainder will 7, right? 35 ones are 35, 42 minus 35, you got 7. Now consider the divisor 35 and remainder 7 not equal to 0. Now here also that case the remainder is not a non-zero, so it is non-zero means 7 not equal to 0. So apply again a division lemma. Now again your divisor become dividend and your remainder become your divisor, right? Now 7 5s are 35, so now it's 0, remainder will 0. So now we move to the step number 3. Continue the process till remainder is 0. Now in our case we got the remainder 0. The divisor at this stage will be required HCF. So now if you got the remainder 0, then your divisor is your HCF. Here divisor is 7. So now your B become your HCF. So B is equal to 7. So the HCF of 455 and 42 is 7. Now remainder is 0, so the divisor will be required HCF, that is 7, right? Now Euclid's division algorithm. So these are some example, you can try yourself, right? Use Euclid algorithm to find the HCF of 4052 and 12576. Remember friends, here your A is become 12,576 and B is equal to 4052. So let A is equal to 12,576 and B is equal to 4052, right? And try to calculate using Euclid division algorithm and find your HCF. Next one is, a sweet seller has a 420 Kaju burfis and 130 Badam burfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of tray. What is the number of that can be placed in each stack for this purpose? So now we have a 420 Kaju burfis and 130 Badam burfis, okay? And she want to stack, a sweet seller want to stack them, so each stack has same number of Kaju burfis and Badam burfis, right? In each stack, right? So now how you arrange that tray like that? So the area of tray will use at least, right? So you just do nothing, just find the HCF of 420 and 130. By using, you got the pieces of the stack of the sweets, right? Now next topic is, some examples are there, okay? So in NCERT book we have example number 2. Show that every positive even integer is of the form 2q and that every positive odd integer is of form 2q plus 1 where q is some integer. So friends, we can solve this by Euclid division lemma. So let's apply Euclid division lemma on that. So let a be a positive integer, right? Here b is equal to 2. Why? Because b is always 2 here 2, because here 2q and 2q plus 1 is given. So b is equal to 2. So possible values of r is less than b and it is always greater than or equal to 0, right? So by Euclid division lemma you know that r, the value of r is always greater than or equal to 0 and less than b. So here b is 2. So possible values of r is equal to 0 and r is equal to 1. Am I right? Now when r is equal to 0, put the value of r on that particular, in this a is equal to 2q plus r. So you got 2q and r is equal to 1, so a is equal to 2q plus 1. Now you know that any number, if you divide it by 2 and your remainder will 0, then this number is called as an even number, and if remainder is 1, then you called as a odd number. So if you divide 2q by 2, so you got remainder 0, so this is even number, and if you add the 1 in even number you got odd number, right? And if you want to divide 2q plus 1 by 2, then always you got a remainder 1. So that's why you can say that 2q is even number and 2q plus 1 is odd number, so hence prove that. Now next, example number 3. Show that any positive odd integer is of the form 4q plus 1 or 4q plus 3. where q is the some integer. So again, like example number 2, applied Euclid division lemma. So first step will same. Now here b is equal to 4. How? Because here 4q plus 1 and 4q plus 3 is there. So you got b is equal to 4. Now applied Euclid division lemma, you got a is equal to 4q plus r. So possible values of r is always less than 4 and greater than or equal to 0. So 0, 1, 2 and 3 are the possible values of r. Now if we take r is equal to 0, in this equation you got 4q plus r, so 4q. So 4q is again an even number. R is equal to 1, so 4q plus 1. R is equal to 2, so 4q plus 2, and R is equal to 3, then you got 4q plus 3. So if you divide this 4q and 4q plus 2, you always got a remainder 0. But if you divide them 4q plus 1 and 4q plus 3 by 2, you got remainder 1. So by that you can say that 4q plus 1 is a odd number and 4q plus 3 is odd number. So we prove our statement that form any positive odd integer is the form of 4q plus 1 or 4q plus 3, right? Now exercise number 1.1, first question. So it is a Euclid division algorithm which already learned. So this is try yourself, okay? You want to find the HCF of 250, 225 and 135 and 38220, 196 and so on, right? Another number problems are there. Show that any positive odd integer is of the form of 6q plus 1 or 6q plus 3 or 6q plus 5. Here simple, you do nothing, just follow the example number 2 and 3. Just here put the value of b is equal to 6. So the possible values of r is less than 6 and greater than or equal to 0. So here b is equal to 6 in example question number 2. It is try yourself. Here is number problems are there. A army contingent of 616 member is to march behind an army band of 32 members in a parade. The two groups are to march in same number of columns. What is the maximum number of columns in which they can march? So there are 616 members each march, but uh, there are army bands are there with of 32 members are in the parade, and behind them 616 members are there. So we have to find the number of columns. So by that we have a same number of members of from the each group. Okay, so maximum number of columns is we can find. So you have to just do nothing, you have to find the HCF of 616 and 32 and you got the number of columns, right? Now question number 4 is something tricky, so I help you to solve them, right? Use a Euclid's division lemma to show that the square of any positive integer is higher of the form 3m or 3m plus 1 for some m. So step number 2, let a positive integer, here b is equal to 3 because here given 3m plus 1, right? Remember here 3, there is a no 3q is given, okay? Here we use a variable m. So b is equal to 3 by Euclid division lemma, here bq plus r, right? So q is the another integer and m is the another integer. Remember this thing, right? Both are the positive integer, but when you square the q, then you got the m. Let's see that. Here b is equal to 3. So applying Euclid division lemma, a is equal to 3q plus r, right? So r is greater than or equal to 0 and r is less than 3. So possible values of r is 0, 1 and 2. Here square of any positive integers are given. So we have to take that square. So here in this equation a is equal to 3q plus r, we put 0 instead of r. So you got a is equal to 3q. Now here use the word square. So we have to take in square both the side. If here is cube, then you have to take in cube both side. But here is the square. So taking square both the side. So a square and 3q square is equal to 3 3s are 9. Square of 3 is 9. Okay. And q square is equal, square of q is q square. Now you take 3 as a common. So you get a square is equal to 3, 3q square. Now put 3q square is equal to m. So is give you 3m where m is the sum integer. So your first form is proved, right? Either in the form of 3m or 3m plus 1. So now next is 3m plus 1. Now in step number 2, if r is equal to 1, then a is equal to 3q plus 1. Okay. Now again square both the side. So you got a square is equal to 3q plus 1 whole square. So a square is equal to 9q square plus 6q plus 1 by using this property. Okay, a plus b whole square is equal to a square plus 2ab plus b square. Now from the first two terms you got 3 common, right? So 3 3s are 9 q, so 3 q square plus 3 2s are 6, so 2q plus 1, because taking 3 common from the right hand side. A square is equal to 3m plus 1, where m is equal to, we putting the value of m here. Okay, 3q square plus 2q, so which is any positive integer. Last, if r is equal to 2, then 3q plus 2, right? So taking the square both the sides, so a square plus is equal to 3q plus 2 whole square. So you got 9q square plus 12q plus 4 using the same property, right? So 9q square plus 12q plus 3 plus 1, we splitting the last term because we divide 4 3 plus 1, right? So 3 is taken here and plus 1 is out of the counts bracket, right? Now 3 taking common, so 3q square plus 4q plus 1, right? So it is again in the form of 3m plus 1. Okay, where m is equal to 3q square plus 4q plus 1 is equal to any integer. So hence prove that which is in the form of 3m or 3m plus 1 form. Now next example, question number 5. Using Euclid division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Remember these things, here is the cube, okay, and here is 9, 9 and 9. So remember friends, you do not use the 9 here, b is equal to not a 9, but we use a 3 only. Why? Because 3 is the multiple of 9. So 9 is the non-prime number. So we use a prime number. So 3. So b is equal to 3. So again it's 3m, 3q plus r, right? And possible values of r is 0, 1 and 2. Okay, I putting the r is equal to 0. So a is equal to 3q. Now taking cube both the sides, so a raised to 3, a cube is equal to 27 q cube, because cube of 3 is 27. Now taking 9 common, right? So you got 9 under bracket 3q whole cube is equal to 9m, where m is some integer and m is equal to 3q cube. Likewise, taking r is equal to 1, then a is equal to 3 cube plus 1, taking cube both the sides. So a raised to 3 is equal to 3 cube plus 1 whole cube. A is equal to 27 cube plus 27 q square plus 9 cube plus 1. By using these properties, a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Now a cube is equal to, taking 9q common, so you got 3q square plus 3q plus 1 plus 1. Why? Because we are taking 9q, so 9q is 1, here 3q and 3q square, so you got 1. So again replace this term use with m, so this is in the form of 9m plus 1. So where m is equal to q, 3q square plus 3q plus 1 is equal to any integer. If r is equal to 2, then a is equal to 3q plus 2. Again taking a cube both the sides, so a cube is equal to 3q plus 2 whole cube. So a cube is equal to 27q cube plus 54q square plus 36q plus 8. By using this property, a plus b whole cube is equal to a cube plus 3a square b plus 3ab square plus b cube. Taking 9q as a common, right? So you got 3q square plus 6q plus 4 plus 8, right? So in the form of, again we replace q, 3q square plus 6q plus 4 with the m, right? So you got 9m plus 8. So hence prove that a cube of any number is in the form of 9m or 9m plus 1 or 9m plus 8.